Let G be a group of order 7 and phi x defined as x raised to the power 4 and x is coming from group, then phi is not 1 1, not on 2, not a homomorphism, and option D is 1 1 on 2 and homomorphism. In this question, we have to test three things: 1 1, on 2, and homomorphism. You can check all four options, and these all four options about 1 1 on 2 and homomorphism. Given condition is G is a group and order of G is 7 and 7 is a prime number, and we know that a group of prime order is always cyclic. This is a theorem, cyclic, and every cyclic group is abelian. Indirectly, property of commutative group is given. We need to check 1 1 on 2 and homomorphism. First, what is the information given? As G is cyclic and order of G is 7. Because G is cyclic, it is generated by, suppose, X. So order of G will equal to order of its generator, and generator gives x raised to the power 7 equal to E. This is the property of generator. And this is least positive integral power when we get E. As phi is given, phi x, the rule for phi is given x raised to the power 4 for all x is coming from G. And suppose here this x is group element and this is generator, so you can change generator as A, avoid confusion. So phi A will be A raised to the power 4 as expression of phi is given. Phi of A square, as this is input, and how phi gives output. Input raised to the power 4. Input is A square. Input is A square. So A square raised to the power 4 gives A raised to the power 8, and it can be written as A raised to the power 7 into A, and this is nothing but E. So this is A. Means A square is A. Now phi A cube will be A cube raised to the power 4, means A raised to the power 12, means A raised to the power 7 into A raised to the power 5, and this is E, so A raised to the power 5. Phi A raised to the power 4 will be A raised to the power 4 raised to the power 4 by defining nature of phi. It will be A raised to the power 16, and it can be written as A raised to the power 7 into 7 into 2, so A square. Phi of A raised to the power 5 can be written as A raised to the power 5 raised to the power 4, and this is A raised to the power 20, and it can be written as A raised to the power 7, 7 and 6. So A raised to the power 6. And last one is phi of A raised to the power 6 will be A raised to the power 6 raised to the power 4, and it can be written as A raised to the power 24. So 7, 7, 7 into A raised to the power 3. And you can check phi A raised to the power 7. So A raised to the power 7 raised to the power 4 it will be a raised to the power 28, and you can write a raised to the power 7, 7, 7 and 7. And this is E, 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 E. So all element of degree higher than 6 will repeat here. So you can check as you put input, you will get output for phi, output, and each output there exists a domain elements or input. For each output there exists a input, and these inputs are coming from G, group G. So phi is onto, and clearly for each input, there is distinct output. So phi is also 1 1. Phi is 1 1. Now here we got 2 points about phi is 1 1 and onto. Now we have to check onto property. As G is cyclic and order of G is 7, because 7 is prime and every prime order group is cyclic and every cyclic group is abelian. If two elements xy is coming from G, then xy will come to or will go to G by closure. If this is an element, apply phi, and by the property of phi, input raised to the power 4, and because G is abelian, so a b raised to the power n can be written as a raised to the power n b raised to the power n when a b are elements of G. So it can be written as x raised to the power 4, y raised to the power 4, and x raised to the power 4 means phi x into this is phi y. That is, phi of xy can be written as phi x, phi y. So phi is homomorphism and these are arbitrary element. So all first three options discard. So correct options is, let G be an abelian group of order 10. Let S equal to G belongs to capital G such that G inverse equal to G. Then the number of non-identity element in S is. 4 options are given for this mathematical problem. Now we are going to solve this problem. S G an abelian group that is AB equal to BA for all AB belongs to Z, and order of G equal to 10. Let S is a set and elements in S are coming from G such that G inverse equal to G. It means self inverse. Means those elements of G which are self inverse will belong to S. Now we have to find non-identity element in S. number of non-identity element in S. To find non-identity number of non-identity elements of S, we have to find. As J is abelian, so I consider a group Zn well known and defined on additive modulo n. Is an abelian group, but we are restricted for order 10, that is consider J10 over additive modulo 10. This is abelian group, J10 abelian group, and elements of Zn are 0, 1, 2 up to 9. Here you can easily verify 0 inverse equal to 0 and 5 inverse equal to 5, because 0 additive modulo 0 equal to 0 and 5 additive modulo 10 5 equal to also 0, and 0 is identity element. 0 is identity element of Zn. So non-identity element in S is only 5. So number of element asked in S which is non-identity and belongs to S is only 5. So option C is right choice. Number of all subgroups of the group Z60 over integer modulo 60 is. It is very simple question, and we have to find the total number of subgroups of Z60 over integer modulo 60. Here you have to remember one statement or formula: total number of subgroup if group is abelian and finite. This formula hold only for this. If group is abelian and finite, then number of total subgroups will be product of P1 plus 1, P2 plus 1, and so on, where Pi are power of prime factorization. Now let us understand what is it. This is Z60 over integer modulo 60. Is it finite? Yes, finite. And abelian? So we can apply this theorem or this statement here. So first, prime factorization of 60 are 2 into 2, 3 into 5. 2 2 is a 4, 4 3 is a 12, and 12 5 is a 60. You can write here 2 raised to the power 2, 3 raised to the power 1, and 5 raised to the power 1. Here, these two, these exponents, 2, 1, 5, 2, 1, 5, play the role of PIs. So, total number of all subgroups of the group Z60 of the group Z60, and operation is integer modulo 60, will be 2 plus 1, 1 plus 1, 5 plus 1. Sorry, 1 plus 1. Again, because prime power are 2, 1, 1, 2, 1, 1. So 1 plus 1, it will be 3 into 2 into 2, 3 to the 6, and 6 to the 12. So there are only 12 subgroups. Only 12 subgroups of the group Z60. Let G be a cyclic group of order 24. The total number of group isomorphism of G onto itself is. 4 options are given to us and we have to find the right one option. As G is cyclic, and order of G is 24. Then we have to find total number of isomorphism from G to G, because these are same group, and composition, same group, and group composition. So it can be considered, this isomorphism can be considered as automorphism. This is automorphism of G, and we have to find total number of isomorphism, that is cardinality of such automorphism. It means how many automorphism can be exist. It means cardinality of this automorphism, and this automorphism is the set all those isomorphism from G to G such that phi is isomorphism, and we have to find its cardinality. G is cyclic and its order is 24. Because G is cyclic, G is isomorphic to Z or Zn, integer modulo n. Because of orders, G is equivalent to Zn. It means we have to find by this cardinality of such automorphism of Zn. And we know that automorphism of Zn is equivalent to this one. Automorphism of Zn is isomorphic to Un. Automorphism of Zn isomorphic to un, and we have to find total numbers of element in un, and it can be easily find out by phi n. Euler phi function. Normally we know it means we have to find phi 24. Phi 24 can be evaluated easily by this formula n, and product of all such divisor which can divide 24, 1 minus 1 upon pi. It means n is 24 and pi are, if 24 can be written as 2 raised to the power 3 into 3. So this is pi, this is p1, or you can say this is p2. So product will be 1 minus 1 upon 2 and 1 minus 1 upon 3. It means 24 1 upon 2 into 2 upon 3. 2 3 is 6 and 6 4 is 24, 4 2 is 8. It means total number of isomorphism are 8. This formula, Euler phi function, can be easily find out or evaluate as this 24 can be written as 2 raised to the power 3 into 3, and this is the product of pi's, and where pi's are divisor of 24, and this is 1 upon pi. Now if we can write 1 minus 1 upon 2 and 1 minus 1 upon 3, and this is 2 raised to the power 3 here and 3 here, then it will be 2 minus 1 upon 2, and this will be 2 raised to the power 3 and 2 upon 3, or 3 minus 1. It means 2 raised to the power, this is ki, it means exponent of primes, minus 1, and this is another exponent, or you can say p1 raised to the power k1 minus 1, or this is p1 minus 1, or p2 raised to the power k2 minus 1, and this is p2 minus 1, and so on. So this is another form of this Euler function you can use somehow, but this is convenient form. So true option is B. Let S3 be the group of permutation of three distinct symbols. The direct sum of S3 with S3 has an element of order. It means we have to find an element of possible order which is given to us. So a useful theorem will help you to find the element of order or possible order. Order of an element in direct sum. And this theorem is the order of an element in finite direct sum of groups is LCM of component of element, component LCM of LCM of order of order of order of or orders of the components of the element. Components of the element. Here S3, direct sum with S3, element is look like G1 comma G2, G1 comma G2. It means this one. So it's and G1 G2 is coming from S3. So order of G1 comma G2 will equal to LCM of order of G1 and order of G2. It means order of components, LCM of order of components. So we need to find possible order of S3, direct sum with S3. We know possible order, only possible order, orders of elements in S3 are 1, 2, 3. So LCM, normally I use this for LCM, and for GCD or HCF I use this round bracket for SCF and square bracket for LCM. So possible LCM are 1, 1, 1, 2, 1, 3, 2, 2, 2, 3 and 3, 3. Here you can check LCM of 1, 1, 1 is 1, 1, 2 is 2, 1, 3 is 3, 2, 6 and 3. It means possible only 1, 2, 3 and 6 are only possible order of an element in S3, direct sum with S3. So which one option is giving 6? Option B is right here.